Thank you for the invitation to talk today. I'm going to give you a very quick overview on the work that we've done to predict spatial variation in arbovirus diseases and their vectors, and then move to talk a little bit about our plans for insecticide resistance. So apologies, the first map I'm going to put up is actually malaria, not an arbovirus at all. But this is important because we've been exchanging a lot of methods between the two disease types. And this particular approach for mapping is something that we want to use for insecticide resistance. So these two maps here have been generated. They're predictive maps, and they've been generated using Bayesian model-based geostatistics, which is a powerful tool. It uses real data from the field, in this case, parasite prevalence, so the top, the falciparum parasite, and then underneath the vivax parasite. It uses real data from the field to fill in the gaps that we have in time and space, and it uses spatial dependence, so it takes account of how close a point where we're predicting data is to a point where we have real data, and it takes account of how close in time real data and predicted data are. It also uses a number of covariates for parasite prevalence, such as temperature suitability for falciparum transmission and so on. And the outputs of these maps are for every 5 by 5 kilometers, in this instance, it produces a prediction that in areas where we have no data, and for each area where it's producing a prediction, for each 5 by 5 kilometers, there's actually a posterior distribution of predictions. So it's providing information about uncertainty in the predictions that you see in the map here. And so that posterior distribution that captures the uncertainty in the estimates can feed through to new analyses. And for example, if you're doing a dynamic or mechanistic model of malaria transmission in a particular area, then the full distribution of results for our prediction for parasite prevalence can go through to that model. But also we've been able to look at the relationship between parasite prevalence and basic reproductive number under control, entomological inoculation rate, and generate predictions for every area for those important epidemiological metrics as well. So this is a really powerful tool that we like to use when we can, but the disadvantage of this tool is it requires huge amounts of data. So the top map was generated using around 25,000 parasite prevalence survey results for Plasmodium falciparum. And it also requires good quality data, so it's quantitative, that's prevalence in this instance, and they've all been measured using consistent methods and cross-sections of the entire community, so we rule out data from pregnant women, for example. So this is a really gold standard data set used in this map, and around 11,000 data points went into the bottom map. So when we come to diseases like dengue, or when we come to vectors, and the next example, these are malaria vectors, we need to take a different approach, because there we don't have tens of thousands of data points collected in exactly the same way for a quantitative metric. So, for example, if you're looking at a vector, you might be interested in abundance, but the idea that you're going to find 30,000 data points where people have measured abundance in the exact same way, it's just not available. So we've taken a more simple approach here. So now we're using species distribution models, and in this case, a boosted regression tree, to predict spatial variation in the probability or the relative probability of occurrence of vectors. And this method uses the environmental variables, the values for environmental variables at locations where we know the vector is present, and environmental variables in background locations or absence locations to predict the probability of relative species occurrence in the locations where we don't have data. But in this instance, there's no spatial dependence used here. So this model is simply extrapolating from environmental data. And here we have an Anopheles gambiae map, and that has been used to then generate a map. So we had each of the major vectors in Africa, we had maps for all of those, and we generated a map which was looking at which combinations are important in which parts of Africa. So that's one way that we've taken that particular method forward. But we've also used similar method for disease mapping itself. So now we're on to the arboviruses. And we use this approach to map, again, the relative probability of occurrence of dengue. And this particular map is the relative probability of occurrence within the known extent of dengue, and it's looking at the suitability for dengue based on the current ecology of the disease and the current environmental variables at the time this map was produced. And using that, we were able to define the relationship between this predicted relative probability of occurrence and the number of apparent and inapparent cases. So we're able to generate population at risk estimates. And this is one representation of that at the bottom there. So this work's been taken forward. I'm not going to talk a lot about this, but we recently published similar work for Zika and Chikungunya. And both of these maps are now looking at areas of environmental suitability. So they're not necessarily saying that the disease has reached a particular area yet. They're both predicting suitability within the ranges of the vectors for these diseases. And then we've used a similar approach to look at Aedes. So this is some work by Moritz Kramer in our group, who again has looked at the environmental suitability for Aedes aegypti and Aedes albopictus and produced these two maps, which are both published. And Moritz is currently taking this work on further. So these maps were produced using data on populations that are persistent in a particular area rather than transient populations. And Moritz has looked at this in a little more detail, so looking at the difference between environments where they're persistent and where they're transient, also drilling down to look at monthly data on the environments in locations, different locations, and then also looking at climate predictions for future climates. So this is now some unpublished work that Moritz is doing to look at the temperature, the environmental suitability for these vectors, and we've just got Europe up here, but he's done this globally. So looking at predictions for what areas will be suitable in the future based on future predictions for climate change. So this is the first part of his work. Then he's also looking at the invasion process for Aedes vectors. So we're not just interested in where is suitable for the vector, we're also interested in where will it arrive to establish in these suitable areas. So he's been looking at invasion processes and using connectivity matrices and a generalized additive model. And what you've got at the bottom here, some preliminary results just comparing real data on past invasions with his model, and he's getting reasonable sensitivity and specificity. I think this was Aedes aegypti, this one. So this is unpublished work, but it describes a little bit what we can do when we take our predictive maps and move them on to the next stages. So next, we're actually trying to improve the model itself. So the boosted regression tree model we use for predicting the distributions of species. Coming back to malaria, we've made some improvements. So this was an original map for the Anopheles dirus complex, and this is our latest one. So the improvements we've made are how we handle sampling bias in the presence data we've got, because it's not comprehensive planned sampling. We're just taking an opportunistic approach and grabbing whatever data's out there. So we've improved how we handle the reporting bias in that. We've also improved how we handle changes through time in the environmental variables that feed into our maps, because the presence data we've got has come through different periods of time, so we want to match it to the environmental variables that were present at the time the data was collected. And we've also improved the way that we handle data where the precision of the location is low. So when we know that data was collected from somewhere within a district, but we don't know exactly where. So we've improved our handling of that and how we capture the uncertainty in that. And so that approach, improving those models, is now feeding through to the Anopheles gambiae sibling species, but more importantly for today, we're moving on to Culex and the vectors of Japanese encephalitis. So this is some of the work that's coming next. And none of us are experts at all on Culex, so if there's anyone in the room who would be interested in working with us on that, we're interested in having some expertise come in. We don't want to produce something that misses important aspects of this species' biology and distribution. So all of the maps that I've presented recognize the fact that they're based on the current ecology of a species, whether it's the virus or whether it's the vector, and the current environmental variables that are present in the world. But we know that species are evolving and they're spreading and the environment is changing. So one of the limitations of our maps was that they were static. So we spent the last 2 years developing a system that now updates these maps. So this is for the disease maps rather than the vector maps, and this has been live now for 1 year. This is a dengue map, and we're producing these, updating them every week. And if you'd like to find out more about this system, I'm happy to talk a bit more, and there's a paper down there that describes a bit more about this process, but very briefly, we rely on a supervised learning process, which means the data coming into us, a subset of it is validated by experts, people such as yourself. So anyone can go and register with our system and validate just a small number of data points coming through every week, and a larger number are then validated by the machine learning system. And we also produce, again on a weekly basis for dengue, some diseases we don't do that often, but for dengue every week, an extent for the disease that, again, experts can come and provide an opinion for any part of this map of whether they believe the disease is definitely present, possibly present, uncertain, and so on. And this is broken down into countries, but also for large countries into states. So now I want to come back to malaria and our more powerful modelling approach, because this is relevant for what we want to do for insecticide resistance. So the same model I've talked about in the very first slide, the Bayesian model-based geostatistics, over the last few years since the falciparum and vivax maps comes out, we've been doing a lot of development work on this and improving the power of this model and the ability for it to incorporate other factors. And so we're now in a stage that instead of producing a flat map for one point in time, we're able to produce a spatiotemporal cube. So for every 5 by 5 kilometers of the world, for every quarter of a year, from 2000 and onwards, we've produced a cube of data. So at every point in that cube, we have a posterior distribution of results for our estimate of Plasmodium falciparum, in this case, prevalence. I say of the world, at the moment it's Africa, but it will be of the malaria endemic world. And so you've got some examples here. This is the prediction for 2000, and this is 2015, but we have plenty of other slices in that cube as well. And you can then look at the difference over time, which is interesting. But also, we've been able now to do more work in how we partition out the environmental and socioeconomic and intervention variables that feed into this map. So it still relies heavily on real data from the field. So 30,000 data points from this time period in Africa inform this map. And spatial dependence is still an important part of this model. But we're also able to look in a little more detail about the other factors that contribute to this variation. So the environmental, socioeconomic, and importantly, intervention coverage. So what we have here is our predictions for the relative proportional contributions of different interventions during this time period to the reduction in Plasmodium falciparum parasite prevalence. So ITNs made the biggest contribution in this time period, and then we have IRS at the top and ACT in the middle there. This isn't to say that this is the relative impact of those three interventions. It's the contribution those interventions have made based on when they were introduced and the coverage they were introduced at. So if you get a very high coverage of ITNs and virtually no coverage of IRS, you're going to see a bigger impact from the ITNs. It doesn't mean that an ITN is more effective. Okay, more effective than spraying one house. So what we want to do now for insecticide resistance is take a similar approach, so now using the Bayesian model-based geostatistics to look at insecticide resistance. And what we've got is we started this work in January, and we're still at the stage where we're collecting data. So we've got, for Africa, around 5,500 data points for mortality in Africa at different points in time and space. And we've got similar amount of data for Asia, but very little for the Americas. So if anyone has data for the Americas, that would be fantastic. as always, we need a lot of data to inform this work, even more so for insecticide resistance, because we're talking about multiple species, multiple insecticides, different bioassay methods, and so on. And what we'd like to do is look at the contribution of different potential drivers of selection on changes in insecticide resistance. And that's in Anopheles vectors. So malaria vectors is how we've started out. But actually, we are interested as well in Aedes. Of course, there are really important differences between Anopheles vectors and Aedes vectors. Genetic background is going to be important. They'll have different habitats, different behavior, and therefore different exposure to insecticides or pesticides or pollutants, whatever the drivers are. However, all of these differences are also true within the Anopheles. So the Anopheles have different genetic background, different habitats, behavior, and exposure to insecticides. So these are all factors that we're going to need to take account in our modelling framework. Therefore, I think our modelling framework is going to be ideal to incorporate Aedes as well. And importantly, there are overlaps in those habitats and behaviours and exposure to potential drivers of selection. So ideally, we would model them together rather than separately. And that is why I'm here today. Thank you.